It would be impossible to begin talking about the ins and outs of AI without a brief background in graph theory. Almost all AI techniques used in games rely on the programmers having an understanding of graphs. Graphs in this context refer to a collection of nodes and edges. Nodes are represented graphically as circles, and edges are the lines that connect them. A graph can be visualized as nodes representing locations and edges as paths connecting them. A graph can be undirected, which means that the paths between nodes can be traversed in both directions, or directed, in which case the paths are one way. Think of this as a difference between two-way streets and one-way streets. Nodes and edges can be drawn where nodes represent coordinates such as those on a flight plan, or as symbolic states where the physical location in the graph is meaningless. Both nodes and edges can have associated values. These values could be the distance between nodes, such as those representing distances in the flight plan, or the time it takes to complete an action, such as a node in the action plan. The ways in which graphs are useful in game AI will become evident as we progress through this course. If you think graphs look familiar, it's because they are. We've already made a graph of waypoints and had our NPC traverse between them. Graphs are so flexible that they can be used for a plethora of applications where you need to traverse from one state to another, whether that be a real state or a conceptual state. In this example, a graph is being used to define the locations in a tile-based game and the amount of effort to move from one tile to another. Values placed on the edges are generally referred to as utility values, whether they represent times, distances, effort, cost, or any other value an NPC might use to make a decision. Let's consider the situation where an NPC wants to move from tile C2 to A2. There are two possible paths. To decide which path to take, the NPC can add up all the utility values along each path. In this case, the utility values aren't about distance, they are about terrain difficulty. Adding up the values along each path reveals that the longer path over the bridge will be less effort. In order to work with a graph, there needs to be an efficient method of searching through the nodes. There are two basic high-level algorithms for searching through nodes. The first is called a breadth-first search. In a breadth-first search, the NPC marks its current location or node as 1. Then it numbers all adjacent nodes to that as 2. Then all the adjacent nodes to them as 3, etc. until the destination node has been reached. It then counts backwards in ones to the start to find a path to the goal. Breadth-first search examines all possible nodes in the graph to find the best path. But due to its thoroughness, it's time-consuming and not optimal. A depth-first search is much simpler and quicker, but less effective. Instead of finding the best path, it finds a path. Beginning at the NPC position, an adjacent node is found and numbered. Then an adjacent node to this is found and numbered. This continues until a dead end is reached, at which time we return to the last node where there was another direction to try and we head off in that direction. It's like the approach you might take to get out of a labyrinth. When the destination is found, the nodes are then counted backwards again to give the path. The most popular algorithm used to find paths in graphs that is used in games because of its efficiency in being able to find the shortest path is the A* algorithm. It's a little more complex than the other two methods and works like this. First, all the nodes in the graph are numbered. We then create two lists, an open list and a closed list. These will keep track of the nodes that we've visited and processed. Each node is given 4 values that are used in calculating the path. First, they are given a heuristic value represented by h. The heuristic is the estimated cost of getting from an individual node to the destination. You can use any method you like for calculating that value. You might use a linear distance or count the number of rows and columns. The second value is movement cost, represented by a g. This value is essentially the utility in moving to the node from another node. This could be based on the actual distance from one node to another, or the cost of traversing a terrain type, like the tile example we looked at with the bridge. We then store a calculation that adds together the h and g values and call that f, and store the node's parent, which is the closest node along the path. Let's take a look at an example. We begin by placing the starting node, in this case 50, into the closed list, as this is the location we have visited. We then look for any neighbours that aren't blocked and aren't in the closed list, and add them to the open list. We then calculate the heuristic for each node in the open list. In this case, we will use the linear distance from the node to the destination. Then we work out our movement cost to go from the starting node to the neighbour. Again, we use a linear distance. Horizontal and vertical neighbours are a distance of 1 away, with diagonal neighbours a distance of 1.4. The cost of moving to those nodes becomes their g value. From that, f, which is h plus g, is calculated. Whilst we are doing this, all the neighbours are linked back to the current node, thus making the starting node their parent. With no more nodes to examine in the open list, we now get the node in the open list with the lowest f value. This becomes a new location to start searching the neighbours again. The new location node is added to the closed list as having been visited. Any neighbours not blocked, closed, or already on the open list are added to the open list. The h value is calculated for any new nodes in the open list. The g value is also calculated, but this time it is the cost of movement plus the previous cost of movement. So in this case, node 32 gets the g movement of 41 plus the cost of moving from 41 to 32, which is also 1. This gives a final g value of 2, and for 32 its f value will be 7. For any other neighbours of the current location still in the open list, in this case 40, a new g value is calculated. If the new g value is less than the current g value, the node's g value is changed and its parent is updated to the current location. In this example, a new g value coming from node 41 would be 1, the g value of 41, plus a horizontal movement cost of 1, thus resulting in a value of 2. 2 is not less than 40's current g value, and so the node remains unchanged. Any neighbour without a parent is assigned to the current location, and the process begins again by looking for the node with the smallest f value in the open list to visit next. The process ends when we are one node away from the end. At this point, we have a link of parents that lead all the way back to the start, which when reversed provide a path from the start location to the destination. Unity uses the A* algorithm for pathfinding in its nav mesh. This construct provides a powerful way for us to program navigation and avoidance into our projects. When you think about it, graphs and their nodes and edges are really a very simple thing. As we progress further through the course, you're going to see them pop up all over the place as they are a staple in artificial intelligence. While there are numerous algorithms to traverse graphs, when it comes to games, nothing beats A*, and you'll find plenty of resources to support it.